All right, we're back. Remember yesterday we learned the power rule, which was fantastic, and we saw a little bit of the chain rule. All right, this time we're going to apply some calc. Number 8 says find the average rate of change of the function over the given interval. Then find the instantaneous rate of change at time 3 and 5. All right, let's start out with the average rate of change first. When you see the word average in our class, that means no calculus involved. The average rate of change is simply rise over run from middle school. Remember, a derivative is a tangent slope, and slope is rise over run, so this all does tie together. What you want to do is figure out what f of 7 is and f of 2. So it's going to be f of 7 minus f of 2. That's kind of like y2 minus y1 over x2 minus x1, which in this case would be the 7 minus 2. All right, let's see what that is. Obviously, 7 minus 2 is 5, so we're good there. F of 7, if you plug the 7 in both times, you're going to get 49 minus 7 plus 8, that's 50. And similarly, if you plug the 2 in both places, you're going to get 4 minus 2 plus 8, that's 10. 50 minus 10, that's 40 over 5. And of course, 40 over 5 is going to be 8. So the average rate of change, I didn't give units in this, but let's say it was meters per second, like in a typical science class. Your average rate of change between 2 seconds and 7 seconds would be 8 meters per second. All right, so average is found without calc. Instantaneous rate of change uses calculus. So, and we asked for two different things. We said find the instantaneous rate of change at time equals 3 and at time equals 5. So we're going to have two different answers here. When you see the word instantaneous, that should clue you in that you have to take a derivative. And the derivative here is going to be 2t minus 1. Again, the 8 is a constant. 2t minus 1. Okay, so there's your derivative. And now if you want to know what the instantaneous rate is at 3 and 5, simply plug the 3 and the 5 in. At time equals 3, whatever it is, seconds, your instantaneous rate of change will be 5 meters per second. And at 5 seconds, it's going to be 10 minus 1. That's going to be 9 meters per second, or whatever the units are. Let's say you were riding your bike and for 10 seconds, and I caught video of you doing so between 2 and 7 seconds of your ride. Your average speed, I'll change units to miles per hour, would be 8 miles per hour the whole way. But if I hit you with a radar gun at 3 seconds and 5 seconds, then your speed would be 5 miles an hour the first time and 9 miles per hour the second time. And obviously the 5 and the 9 don't have to be your average speed. When you get caught speeding by a police officer, hopefully that's never happened to you, usually they don't clock you at your average speed of the trip. They clock you when you're going fast. So the numbers don't have to match. The 8 does not have to be halfway between these. They're just all independent answers. Okay, let's move ahead. Number 9. Somehow I suddenly feel like a science teacher. This is crazy. I gave you a position time graph, and I'm asking you, first of all, when is the particle moving to the left? Okay, and again, I'm assuming that we're just moving left and right, say on an x-axis kind of situation here. So moving to the left would be if your position is decreasing. Well, you're moving to the left between 3 and 5, right here, because you're going from a position of 3 to a position of 2, so that's to the left. When we say 3 to 5, I write it in interval notation with curly parentheses. You're also moving to the left right here between time is 7 and time is 8. So between 7 and 8. And we put the symbol in the middle of a U, which is the union. That means or. So the particle is moving to the left between 3 and 5 or between 7 and 8. All right, where is the particle, or I should say, when is the particle moving to the right? Well, that's when you have basically a positive slope. So that's between 0 and 3, but also between 8 and 9. So we've got 0, 3, union with the interval 8, 9. And when is the particle standing still? Well, technically, standing still means you're not moving left or right. So that would be this part right here and this part right here. So we're looking at 5 to 7, union with 9 to 10. So far, so easy. I mean, that felt more like 9th grade science than 11th or 12th grade calculus. But hey, it's all good. All right, it's going to get a little weirder, though, as we move ahead. All right, I took the exact same position graph from number 9, and this time we want to make a velocity graph out of it, which is something that you do in science class. And here's the first thing that's kind of really powerful that links our two classes together, calc and physics. Velocity is the derivative of position. Whoa. It's true. You take a derivative, and derivatives are slopes. So if you look at the position graph, the slope of that first little segment there is 1. You're going up 1 and over 1, which means that your velocity would be 1 for the first 3 seconds of travel. And again, there's a corner right here, so therefore this has to be an open circle because there's no derivative. In fact, there's no derivative in several parts of this. In fact, this is very herky-jerky motion. You would never want to ride in a car with somebody driving like this. You would have some serious whiplash because right here in this portion, your slope is -1/2, so the derivative is -1/2. So you're going to be here for the next 2 seconds, or next 2 units of time, whatever they happen to be. Then you flatten out, you're standing still, so your velocity is 0 for 2 seconds. So this has obviously got a lot of jump discontinuity in it. Then the driver goes crazy. That's down 5 and over 1. Oh, genius. I didn't even leave enough space on my graph. We're just going to fake it here. That's -5 right there between 7 and 8. Then the slope becomes +2 between 8 and 9. And finally back to 0 for the last second, or last unit of time, whatever it is. So that's your graph of velocity. Really, in real life, nothing can move like that. If you go from 30 miles per hour to -10 miles per hour, you have to go through all the numbers in between. So, this is not continuous motion. We will see that more often coming up soon. All right, so that's our very first conversion between position and velocity using the derivative. In fact, I just want to speak briefly to the people who are in physics. If you're not in physics, don't worry. This is not going to be anything that's going to ruin your math. But this is cool. Okay, position is just going to be f of x. A lot of times in the science books, they'll call it y, or height, distance above the Earth. Sometimes they'll call it h. But position is just the original function. When you go from position to velocity, you take a derivative. So the velocity is the first derivative. If you take another derivative, now you're at acceleration, which is the second derivative, f double prime of x. Now, if you talk about the units, the United States is still kind of resistant to the metric system outside the scientific community. We're only one of 3 that don't use it in the world. The other 2 are Myanmar and Liberia, which actually we formed Liberia, so that's probably why they use it. But anyway, most people in the world use meters for position. Velocity is meters per second. And acceleration is meters per second, or meters per second squared. You think about gravity, -9.8 meters per second squared, downward direction. But every time you take a derivative, you gain a per second or a per unit of time. Isn't that wild? And that could be very useful in physics. I don't know if you noticed this or not, but all the physics formulas are derivatives of each other when you go from position to velocity to acceleration. So if you memorize the first formula, and you can do the power rule from our class, you don't have to memorize the second and third formulas. So that's pretty cool. Just wanted to mention that. More on that later. All right, back to my lesson. Number 11. The velocity is graphed below. This is a different graph. When does the particle move forward, move backward, stand still? Again, that doesn't seem too hard. Since this is a velocity time graph now, remember that the first graph was position time, but this is velocity time. So if you want the particle to move forward, you simply want it to have positive velocity. Where does that happen? Well, it happens between 5 and 8. Right in that green section where the graph is above the t-axis in this case. Again, notice I'm curling the parentheses because it's not really moving forward at 5 and at 8, just in between them. When does it move backward? Well, it moves backward when you're below the time axis, so that would be between 0 and 5, union with the interval 9 to 10. And finally, when is this thing standing still? Well, standing still literally means velocity is 0, so you're looking at right there between 8 and 9. And some people are going to actually make a case for right here at this brief nanosecond at time equals 5, and I would accept that as well. To be honest, I'm not overly picky if you have the time equals 5 there. The 8 to 9 has to be there. Really, I guess it's standing still when you change directions, just for a split second in time. So we'll use both. All right. More questions about the same graph. When is it speeding up, slowing down, accelerating, decelerating? Wait, isn't that redundant? No, it is not. Wait, what? I thought speeding up meant, acceleration. Aren't they the same? No. Whoa, this is about to get weird. Okay, when is this thing speeding up? Well, it's speeding up between 0 and 2, between 5 and 7, and between 9 and 10. When you think about it, that makes complete sense because this is a velocity time graph. If you're driving a car and you hit somebody at 0 miles per hour, then you didn't really hit them. They ran into you because you're sitting still. So the time axis, what normally is the horizontal x-axis, in science it's the t-axis. If you're along the time axis, you don't have any speed. As you move away from the t-axis, either in an upward or downward direction, you become more dangerous to yourself and others. If this was instead of 2 and 4, if it was 20 and 40 on the scale, and you're going 20, 40, 60 miles an hour, and you're heading up, you can hear the engine revving. Yeah, you're speeding up. But conversely, if you are along this portion of the graph, you're getting more dangerous as well. Negative 20, negative 30, negative 40 miles per hour. I've never been in a car going negative 40. I'm sure it's terrifying. I don't think I ever want to have that experience. But yeah, you're speeding up. So you're moving away from the axis. Well, then slowing down would make sense. You'd be heading toward the axis. And that would happen right here and also right here. So that's going to be between 4 and 5 and also between 7 and 8. Oh, and also between 2 and 3. My goodness. Right, so there's 3 places where you're heading towards the time axis. You can see them. All right, when does a particle accelerate? And it seems like that's the same thing as speeding up, as I mentioned, but it is not. You are accelerating when you have positive slope. So you're accelerating here and here, between 2 and 3, and between 4 and 7. And at first that seems a bit crazy. People are like, whoa, wait a second. So you're telling me that between 4 and 5, right here. And I'm like, uh-huh. You said that you were slowing down, but you're accelerating at the same time. Yes, that's exactly right. What? That's crazy talk. No, it's not. You are accelerating and slowing down. We're so used to in our own culture of automobiles that we're almost always in drive. In fact, I only put my car in reverse once a day. I have a side-facing garage at my house, so I pull out, I make a quick, one-point turn, and I go down my driveway head first, so I can see. And when I get to school, I get here early, and I I park in the parking lot, I pull all the way through so when I leave I can just pull straight out, I don't have to back it up. I'm hardly ever in reverse. And when you're in drive, you're up here all the time. Your velocity is always positive. Whereas if you're in reverse in your car, you're down here. And so we're used to figuring that if you speed up and you accelerate, you can hear the engine, you're getting faster. That's normal because we're used to being in drive. But when you're in reverse, the brake actually accelerates your car. Whoa, it's true because you're going from -10, -9, -8 miles per hour. The numbers are getting higher, but you're slowing down. All right, so when does this decelerate? Well, it decelerates when the slope is negative. That's going to be between 0 and 2, 7 and 8, and 9 and 10. There was one more thing I wanted to mention. I forgot to put the question on here. It might be on the internet, but it says, when is the speed the greatest? Translation, when are you farthest away from the t-axis? And the answer is right here at 2 seconds. Your speed there is 3. The speed right here is only 2. So you have to watch what the teacher asks. If I say, when is the velocity the greatest? That would be right here at 7 seconds. If I say, when's the speed the greatest? It's at 2 seconds. Because speed is the absolute value of velocity. Speed can never be negative. If I'm an idiot, maybe you think I am, who knows, but if I'm a true idiot and I'm in a parking lot at 3 in the morning and there's nobody around and there's no telephone poles and I decide to go -30 miles per hour, I don't know what the speed limit is in a parking lot, probably 10, and a police officer sees me and pulls me over, if it was called a velocity ticket, I could fight it in court because my velocity was -30 and the sign said 10, so I'm below. That's why they don't call it a velocity ticket. They call it a speeding ticket because my speed is 30, absolute value. And the sign said 10, so they ticket me, as they should. Because you shouldn't go 30 miles an hour in reverse. That's just moronic. Okay, that does it for day number 2. One more day to go. And the third day, this is kind of exciting. We're going to bring back more physics. We're even going to bring some econ into the class as well. So it's going to be good. We're going to really use derivatives for practical things. All right, see you then.